To understand the case of a matrix A with real eigenvalues and real eigenvectors, we can see A as a linear transformation that can take a vector X and transform it into a vector Y. For example, X0 is transformed into Y0 through the matrix A. In this case, X0 and Y0 are pointing in different directions and they have different magnitudes. But what if we try a different value for the vector X? So we can run this experiment. We get the vector X0, we rotate it an angle theta and observe the transformed vector Y. So we take X0, multiply by the rotation matrix R, and we obtain X. And then X is transformed into Y through the matrix A. We start with a vector X equal to X0 and Y equal to Y0. And then we increase the angle theta. X and Y are pointing in different directions until we find the first singularity. Here, we're in the space described by the first eigenvector, Q1. X and Y are collinear, but they're pointing in opposite directions. Therefore, the eigenvalue is real, but negative. The absolute value of the eigenvalue will be greater than 1 because Y is larger than X. If we keep increasing the value of theta, X and Y again will have a different combination pointing in different directions until we find the second singularity. Here, we're in the space described by the eigenvector Q2. X and Y are collinear, pointing in the same direction. Therefore, the eigenvalue will be real and positive. And again, as Y is larger than X, the eigenvalue will be greater than 1. If we keep increasing the value of theta, then we complete the set of X and Y pointing in different directions. And when we pass through the space described by Q1, and again, X and Y will be collinear. And we will do the same when we pass through the space described by Q2, and X and Y will be collinear. And we observe the collection for all the points of X, they describe a circle. If we observe the collection for all the values of Y, they describe an ellipsoid. The axes of the ellipsoid correspond to the eigenvectors Q1 and Q2. Through the axis Q2, we're going to have the largest stretch of that circle into that ellipsoid. That's why the eigenvalue lambda 2 related to the eigenvector Q2 will be the largest one. As a summary, I am presenting here the values of X and Y for the first singularity. So as you can see, Y is a scale version of X, and the scaling factor is lambda 1, the eigenvalue. For the second singularity, we have X and Y, and once again, Y is a scale version of X, and the scaling factor is lambda 2, the largest eigenvalue.